Hello, thanks for joining me as we continue this electrochemistry unit, looking today at introducing the concept of electrode potentials, where we're going to investigate the concept of electrode potential and describe galvanic cells. So moving on from the previous lesson, we've finished looking at electrolytic cells, where we were taking electrical energy and using that to drive a chemical reaction, taking electrical energy, converting it into chemical energy. We're now going to look at a different kind of electrochemical cell, which is called galvanic or voltaic cells, where you're doing the opposite of that. You're taking the chemical energy and using that to generate electricity. So let's first introduce this idea of a redox equilibrium, two phrases we're pretty familiar with. Two chemically related species exist in a redox equilibrium occurring when rate of electron gain equals rate of electron loss. So far we've been describing these redox reactions, these redox half reactions, as either a reduction half reaction or an oxidation half reaction. More accurately, they're existing at an equilibrium. If we think back to that terminology, that's referring to the rate of the forward reaction equaling the rate of the backward reaction. So there's no observable change, but both directions are occurring at the same rate. Thus, no observable change. So then when we talk about the idea of redox, we're talking about electron transfer. So putting these two ideas together, essentially what we're saying is that if we consider this equilibrium system, where I place a magnesium rod, for example, into a magnesium ion solution, we have a forward reaction occurring, where our magnesium ions are being reduced to the magnesium metal. And then we have the reverse reaction going, the backward reaction, where the magnesium atoms are being oxidized into the magnesium ions. And at a certain point, an equilibrium is going to be established. So let's look at both those reactions occurring with my little diagram here. So essentially, we put the magnesium rod in the magnesium solution. We have the metal atoms entering the solution. So we have the oxidation occurs and the electrons are left behind on the rod. And then the cations in solution can also undergo reduction back into the metal and be deposited back on the rod. So at a certain point, the equilibrium is established where the oxidation reaction is occurring the same rate as the reduction reaction is occurring. This equilibrium creates a flow of charge. We're dealing with charged species. We're dealing with cations moving around. We're dealing with electrons moving around. So popping this into a solution, we have a flow of charge, which creates an electrical potential difference established between the metal and the metal ions. So look, without getting too physics-y, electrical potential difference, I've just sort of got a simplified definition here, is the difference in the amount of work, or you can think, in terms of energy, might be not entirely correct, but what we can use for now, to move a unit of electric charge, and it's measured in volts. So, maybe we can just simplify that to thinking in terms of, it's an electrical energy. What else do we have here? However, this potential difference cannot be measured directly because we know that oxidation reactions require reduction reactions, so we can't measure one without the other. But we can measure the difference in potential between a metal ion system, such as our magnesium system here, and we can compare that relative to another system, where we can define this as the electrode potential. Given the symbol E, it's the voltage, so that electric potential difference measured for a half cell when compared with another half cell. All right, let's think of this redox equilibrium in terms of reactivity. We have here that different metals have different reactivities. Some readily form ions and some do not. So what this is going to do is this is going to affect the position of equilibrium in our redox equilibrium. We can think back just in terms of general equilibrium, where the equilibrium might lay more to the left-hand side, more favoring the reactants, or it may lie further to the right-hand side, where we're favoring the products, and we've got more products at the equilibrium. Same concept applies here, just with a redox reaction. The redox equilibrium position is different for different combos of metals placed in solutions of their ions. So let's consider what the position of this equilibrium is saying about the reactivity of the metal. So this reactivity position is implying, is it a reactive metal or is it not a reactive metal? You know, if we think in terms of a metal reactivity, metals react by losing electrons. Metals react by undergoing oxidation. So if we have an equilibrium lying one side or the other, it's gonna give implication about that. So let's consider where we've got a reactive metal, you know, a more reactive metal, relatively speaking. In this instance, equilibrium lies further to the left. Well, let's think about that. We've just said that we have a reactive metal. So the reactive metal is going to want to stay in the oxidized form. It wants to react, it wants to lose the electrons. So when we draw our redox equilibriums like this, where we're showing the redox reaction, well then we're going to end up with more of the ionized form because that is a more reactive metal. It doesn't want to exist as the atomic form because it's reactive. Now just bear in mind, I'm always going to be speaking relative to the reduction as the forward reaction. Right? So whenever I'm talking about equilibrium lying further to the left or further to the right, I'm always being consistent where I'm saying we're writing out the reduction reaction as the forward reaction. We'll talk about that a lot more as we go through. So what does this imply? This implies that we got more zinc ions than we do zinc solid. So we have an equilibrium lying to the left. Therefore, we can say that this is difficult to reduce. Conversely, this is difficult to oxidize. So let's think about what that's implying for the electric charge on our electrode here. There is an electron surplus on the zinc metal as equilibrium lies to the left. So as we have more zinc ions in the solution, we have, therefore, you know, if equilibrium's on the left, we've got more electrons, which creates a surplus of electrons on the zinc metal. So that's what I've shown here. The negative is representing the surplus electrons in the zinc metal. The positive represents the extra zinc ions in solution. So that's if we've got a reactive metal. Let's consider the converse of that. If we have quite an unreactive metal, well, this is just the inverse to everything I've essentially just said about the reactive metal. The unreactive metal does not want to be in the ionized form. The unreactive metal doesn't want to lose electrons. It's unreactive. So we're going to stay very much more in the atomic metallic form. So what that means is that our equilibrium here is lying much further to the right compared to our reactive metal because it's wanting to stay in that atomic form. So what does this mean? This means that it's easy to reduce because it wants to go in this forward direction. Or we could say the opposite, it's difficult to oxidize. So that has the opposite situation over here, where we end up with a surplus of positive charge on the electrode. So the copper is less reactive, so equilibrium lies to the right-hand side. So the copper ions remove electrons to form the copper atoms on the surface. This gives a positive charge for the electron deficiency in the copper metal and a surplus of anions in the solution. So we have the copper very much wanting to go into that atomic form, which is going to give a surplus of anions in solution, make that more negatively charged. And we have a positive charge because we now got a electron deficiency on the electrode as opposed to having a electron surplus. So, you know, implying that opposite charge. So the absolute electrode potential, so the amount of voltage absolutely on one of these systems here, is thought to be a result of a buildup of charge between this electrical double layer that occurs between the electrode and its solution, depending on where that equilibrium position lies, as we just discussed. But reduction requires oxidation, oxidation requires reduction. So each reaction is only constituting a half cell of a galvanic cell. So you've got to put two of these together to get this whole system to be running. So let's have a look what this looks like. We have a galvanic cell. So again, this is a type of electrochemical cell where we're made up of two of these half cells that we just described. Let's discuss the features. A type of electrochemical cell that converts chemical energy into electrical energy. They're also called voltaic cells. I'm just going to stick with galvanic cell from this point forward. But, you know, electrochemical cells, our electrolytic cells have been talking a lot about as one kind. This is the other kind. And it's all about which way that energy conversion's going. In the electrolytic cell, you've got to put electrical energy in to drive a chemical reaction. In our electrochemical cells, we've got the chemical energy that can undergo the redox reaction to generate the electrical energy. Can consider it as the opposite of electrolytic cell. There we go. That converts energy to electrical energy to chemical energy. So it consists of two separately contained half cells joined via a circuit and a salt bridge. So that's what we see here. This is one of these half cells. That is another one of these half cells. The circuit has to be complete. So we have a wire with a voltmeter, we can measure that voltage, and then a salt bridge whose purpose we will discuss momentarily. So let's go ahead and draw one here. Let's draw a galvanic cell consisting of the two that we just looked at, consisting of this zinc and copper half cells. So when we draw them, and we will be drawing plenty of these, we want to, how do I get the straight line? I've forgotten how to do this. That one. We want to draw a half cell like that. We want to draw the other half cell, and these are separately contained from one another. We're going to pop our metal electrode in there, and that's in our metal solution. Now we will be looking at other kinds of half cells that aren't metal and metal ion, but for now let's just keep it simple and introduce this one that we've just introduced. So we've got the metal rod and we have the solution. We've got to connect these with a wire that we can run, I can do better than that, that we can run through a voltmeter because we want to measure the electrical energy that we're producing. And then this is completed via something called a salt bridge. We'll discuss what this means in a moment as well. Brilliant. So let me get back to my regular pen. I'll put the V there for the voltmeter. So we want to look at combining these two half cells. So in one of them, we're going to have the zinc redox reaction. The other one we're going to have the redox equilibrium. And the other one we're going to have the copper redox equilibrium. So look, let me say that we're going to pop the zinc on the left-hand side. Doesn't really matter which side you do, as long as you are consistent with everything. So I'll say that's my zinc solid, and then down here we're gonna have zinc ions, aqueous. You know, that could be a zinc sulfate solution or something like that. Then over here we're gonna have our copper, our copper solid, and our copper, what are we doing? 2+ aqueous solution down there. So just like our electrolytic cells, there's lots of information that we can put onto these diagrams. So let's consider about what's occurring, because we said, you know, we got a redox reaction, we have a transfer of electrons. So one species needs to be undergoing reduction, the other species needs to be undergoing oxidation. So for now, let's just think in terms of this in terms of our reactivity. Now we'll put numbers to this later on, but let's just think conceptually for now. So we've said that the zinc reactivity metal, the equilibrium lies further to the left. It very much wants to exist as the zinc ions, meaning it's difficult to reduce. If it's difficult to reduce compared to something that's easy to reduce, this is not going to be reduced, this is going to be oxidized. So our zinc is going to be undergoing the oxidation half reaction. So we're going to have the zinc solid going to the zinc ions and to electrons. So essentially what we got over here is we've got the oxidation half reaction. What am I trying to do here? I might just do this, write it out here. Now, we know from an oil rig cap that oxidation always occurs at the anode. So that must mean that this is our anode. So the electrons are being lost here as the zinc is converted into zinc ions in an aqueous solution. And we can show, just as we did in our electrolytic cells, we can show the flow of electrons through the circuit into here. And then on the right hand side, we said, let's think conceptually again, we said that the copper is unreactive. So that means the copper very much wants to be the atomic solid, the metallic solid. So it's easy to reduce, it's difficult to oxidize. So if you put something that's easy to reduce with something that's difficult to reduce, then clearly this one's going to be oxidized and this one's going to be reduced. Now, like I said, later on, we're going to put all sorts of numbers to this so that we know exactly what will undergo which process, but let's just keep it conceptual for now. So our copper 2+ ions are going to be reduced to the copper metal. Now, this is a reduction reaction. So this is occurring at the cathode, an oil rig cat. Oxidation always occurs at the anode. Oxidation is always loss of electrons. Reduction always occurs at the cathode. Reduction is always gain of electrons. Now here's something that's very important, which is different to the electrolytic cells. So unlike our electrolytic cells, where we have the positive is the anode, the positive electrode is at the anode, in this instance, our oxidation reaction, let's just think, I'll write it up here again, such an important little phrase, an oil rig cap. If we have oxidation occurring at the anode, in this instance, our anode has the surplus of electrons. So our anode ends up being the negatively charged electrode. Conversely, our cathode, where our reduction occurs, so we said that, over here, our system that's easy to reduce, this ends up with the positively charged electron deficient. So we end up with the positively charged electrode being the cathode, which is the opposite to what we see in the electrolytic cells. So really important when you've got the electrolytic cells, the positive is the anode. When you've got the galvanic cells, the positive is the cathode, for the reason that we've just discussed here in terms of this redox equilibrium. So that means that, in fact, my anode over here where this zinc reaction occurs is going to be the negatively charged electrode. So I'll pop that there, negatively charged electrode, positively charged electrode over there for the cathode. So you can think of this again in terms of, it's essentially the opposite of the electrolytic cell. So if we had positive anodes in the electrolytic cell, in the galvanic cell, which is the opposite process, we have positive cathodes. Right on. So we need both of these half reactions to occur in order to get this redox reaction occurring. Let's find where we were. Let's talk about these other features of the galvanic cell, starting with the wire. Not referring to one of the greatest series ever made, but instead referring to how we can actually complete the circuit and connect the two half cells. So the wire is connected to a high resistance voltmeter that connects the two electrodes, allows electrons to flow around the circuit from the half cell that is more difficult to reduce, therefore easier to oxidize. So what we saw here, where the electrons are lost and they flow through the wire to the half cell that is easier to reduce, that wants to gain those electrons. And then we talked about the charge where the anode is negatively charged, the cathode is positively charged, which is counter to the electrolytic cell. But importantly, an oil rig cat is always true. Oxidation always at the anode, reduction always at the cathode. These charges are just inverted because we've got this electrical double layer based on this redox equilibrium that we've discussed quite a little bit now. Then we have the salt bridge. So the purpose of the salt bridge is to also complete the circuit by allowing the half cell solutions to remain neutral. So let's think about what's going on here. In our oxidation half cell, I might get a different color up. In our oxidation half cell, we're going to have another ions. Let's say we got sulfate ions in there as well. As this oxidation reaction occurs, we're increasing the concentration of our Zn2+. We're getting more and more Zn2+ in there, which is going to make this more positively charged, which if it gets too much, the reaction will cease. So the salt bridge is a bridge between the two half cells that contains a salt, which is able to counteract this increase in charge. As the concentration of ions change in the solution, they are replaced by the salt bridge to maintain ionic balance. So it's made of a strip of filter paper soaked in an ionic salt, for example, saturated potassium nitrate solution. So importantly, there are anions on the salt bridge and there are cations on the salt bridge. You know, it could be potassium, it could be, what did I just say in that example? Potassium nitrate. It's just got to be something that's soluble. So what happens is as this positively charged species increases in concentration, the salt bridge can counteract that by putting more negatively charged anion in there, allowing the reaction to continue. And the same thing over here with our reduction reaction. As our copper ions are going out of solution, let's say we've got copper sulfate over here, that means this is getting more negatively charged, which again, if it gets too negatively charged, the reaction is not going to keep going. So as the copper ions are removed out of solution, it gets more negative, the salt bridge can counteract that with a species. Potassium in this instance, because the potassium is way more reactive than the copper, so it's not going to be reduced. So it can counteract that charge and complete the circuit. So they are all our species in our galvanic cells. So lots to include. Two half cells, we've got the flow of electrons, and we've got the salt bridge to counteract that increase in charge in the solutions of the two half cells. So we can use some annotations to represent the half cell that we have. So we can write it like this. We'll get a nice purple color. We write, by convention, we write the anode on the left, which is what I've drawn over here. So in this instance, I've got an anode that's taking zinc solid and converting it to zinc ions. So I'm showing that process there, like that. Now my other half cell, we have copper ions that we're reducing to copper. So I can show this like this, aqueous and solid. So what's going on with my annotation here? I'm showing the difference between the phase boundaries with a single line. So the fact that we're going from a solid to an aqueous. Same thing over here, single line. And then I am separating my two half cells with a double line, and that's showing my salt bridge. So this whole galvanic cell, I can annotate as that, and that's showing this redox process. If you've got species, as we'll see later on, if you've got species that are all in the same phase, you wouldn't separate them with a phase boundary, you just separate them with a comma instead. Brilliant. So what have we got back over here, the last little bit? Importantly, what I've said a few times, we can't measure these individual electrode potentials. We can only measure them relative to each other because you need one reduction to occur with one oxidation. The processes need to occur simultaneously. So we can start putting figures to this, which is what we'll do moving forward, by measuring each of them against a standard to determine usable values, such as the standard hydrogen electrode, the SHE for short, that we'll look at next time. But look, that concludes our introduction to electrode potentials. We've defined the electrode potential, what's referred to as reduction potential. We'll talk about that more next time. And the standard cell potential being the voltage that is generated from this whole galvanic cell together. As always, tasks. If you want some consolidation, pause and give it a red hot try. Fantastic. Thanks for your time as always. I'll see you next time. Have a good one.